let's talk about this one. So you're supposed to find that area, the shaded area. How are you going to do that? It looks weird because it's an area that's above a curve. But remember, we're looking to find some of these weird areas by subtraction. So what do you think, Maria? You have an idea? Mm-hmm. Hmm. Mm-hmm. Right. Okay. You're on the right track. You can even make it easier though. What I guarantee what's conceptually challenging people on this one is the fact that would everybody agree in quadrant one from 0 to pi fourths, it wouldn't be so bad, right? It's just the red function on top of the blue function, right? So it's the area under the red function minus the blue function. Everybody get that? The red function is just a constant function. Like if I'm just going to look in quadrant one, here's the red function. Whoops. Let me. So you've got this area. You've got the area under the constant function y equals the square root of 2, right? That's just a rectangle. It's just going to be square root of 2 times pi fourths is that area, right? Is the red area. Yep. Yeah. Okay, what is it? Well, you can potentially do that too. Yeah, you're right. We can. That's not even what I was talking about, but you can. You're right. You can use symmetry on this also. But what I guarantee what's the way I think you want to look at this. Let's focus on just the interval from 0 to pi fourths, and then we'll talk about why we can just extend that. There's no reason it's not going to extend all the way back to negative pi fourths, right? Isn't the shaded area just the total red area, which is all that stuff, minus the blue area, which is let's not make it blue. Let's make it like purple, minus the purple area under the curve. Red minus blue is cyan, right? Or red minus purple is blue. Everybody agree? Okay. It is. It is. And here's the reason why, because you don't have to worry about the fact that make this more complicated and think, oh man, this one's underneath the axis. So we've got to add up this area and that. It doesn't work that way. It's always just the top curve minus the bottom curve. And here's why, because the top curve, if I add up the area between negative pi fourths and 0, again, I'm just going to get the constant area of that rectangle there, correct? Okay, but I'm going to subtract. Oh, hang on, I've got to subtract from that the area under the blue curve. What can you tell me about just that area right there below the x-axis in quadrant 3? Positive or negative? Negative. So if I'm subtracting that negative area, the math gods take care of it for me, right? I just get this positive area underneath, that's this rectangle up here. I'm talking about this one, right? There's the area under the red function from negative pi fourths to 0, some positive amount, right? Minus this negative amount. Subtracting a negative is adding, right? So it did it correctly. We added up the entire blue area as positive as we should have, because the area between the curves is all positive. Everybody get that? Wherever the red curve is on top of the blue curve, the area between those is added from top to bottom, so that's positive, and from left to right. Okay? Like we could look at it, let's look at it on Desmos. I can see that didn't do the job. Let me try this. Let's look at this on Desmos here. Okay, let's see. Properties of definite integrals. Let's try that one. Yeah. Okay. So let's look at, I'm going to make f of x equal square root of 2. So the area from negative pi fourths to 0, I'll make that 0, is just, we're looking at that area. I can zoom in here, right? That's the area we're looking at. Okay, that's the square root of 2. That's negative pi fourths. That area is 1.107 blah, blah, blah. Positive. Agreed? Okay. What's the area under the curve? Let's try a new curve. Let's try the function. I'm going to mess this whole thing up here. Let's call this, if I use g, no. Okay, g of x equals secant x tangent x. Why is it? I don't think I need to. Oh, maybe that is it. Yeah, you're right. Okay. So there's my function, right? And let me go ahead and make the x-axis go from negative pi fourths to positive pi fourths. Okay, so say it again. That's odd symmetry, yeah. So if I want to add up the area, let's let b equal the area under g, the function g, from a to b. I'm just going to change this a little bit, from a to b. Okay, and what do I get? Negative 4.142, blah, 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 right? Okay, that's that little area right down in there, okay? And it's not going to shade this very well because I'm messing this whole thing up, but you get the idea. You'll have to imagine the shading yourselves. Okay, now let's calculate the function f of x minus g of x. Okay, I'm going to call that h of x. Yeah, this is going to be pretty cool. This will work. Okay, so now we're going to add up the area under that function. So this is going to be under h from a to b. What do you know? Look at that. It's 1.524. It's, everybody see, it's just going to be that number minus that negative number. So I'm adding up those two areas. It did it, right? It did what it was supposed to do. It added up, what we just added up is all of this area, let's see, this area right here. Okay? That's all we had to do, was just subtract the bottom function from the top function. The math gods take care of the signs so that it's always going to add up the area underneath a top function, bordered on top by a top function and below by a bottom function. It's always going to add that area up as positive. Now, if those had flip-flopped, if the red function and the blue function had crossed, then where the bottom function ended up being on top, it would have calculated that area as negative because it would have been adding it up from the blue function upwards to the red function. And that's our negative convention for adding area. How do we add up area as positive? From right to left and from top down, okay? The implication normally is if there's only a single curve, well then if I'm adding up the area under f of x, isn't f of x the same thing as f of x minus 0? right? So I'm really adding up the area between the two functions f of x, y equals f of x, and y equals 0, which is the x-axis. Everybody get that? Right? You see what my point is there? Like if I'm just adding up the area under just the red graph, I'm going to stop adding up the area from top to bottom at 0. Because again, f of x is the same as f of x minus 0, right? So I'm adding up the area between the two curves, red function and x-axis, which is the default. That's 0. That is an area of 0. Does that make sense? I mean, you never think of it that way. I don't think I've ever explained it that way to anybody, but you can see how those two cases are consistent. Now, we're just changing it. Instead of adding up the area just under f of x, meaning between f of x and 0, we're adding up the area between f of x and g of x. So the bottom limit of the area, the bottom boundary of the area is no longer the x-axis. Now it's the blue function. Okay? So what's the moral of the story? The area bracketed by two curves is always going to be the area of the top function under the top function. Well, yeah, the area of the top function minus the bottom function. The definite integral of f of x minus g of x, if f of x is the top function and g of x is the bottom function. Okay? And of course, that's going to continue into quadrant, for values greater than 0, right? Because again, now we're just doing red minus blue, only now that gives us a smaller area because we're subtracting a positive blue area from a positive red area. Okay? And so we can see that. Like if I just shift this over to, let's just shift our limits of integration from a is going to become 0 now, and b is going to become positive pi fourths. What do you find? Okay, then you find that the area under the top function is same as it was before, right? They're symmetrical, so it's just 1.1107, blah, blah, blah. The area under the blue curve now is positive 0.4142, blah, blah, blah. So when I subtract those, look, I get something slightly less than 0.7, which we see. That's a smaller area than that whole thing is, isn't it? Okay? Does that make sense? Sort of, kind of, maybe. How would I, let's just try a sample problem. So how would I do this then? What if I wanted you to find, let's just say something like this, okay. How could I set up an integral to capture the, let me do one, I'm gonna change one thing here. Let's change this guy. I wanna change him. Why is it not letting me do that? Okay, undo that. Undo that. There we go. Okay, I want to change this blue function so it looks like this. How about that? Find the encapsulated area as an integral. Everybody just think about it. Don't say it out loud real quick. Everybody just think about that and try to find what's the area bounded by the three functions, red, green, and blue. How would I find that? The red's just that vertical line, right? So it's not a function, but by the red line and the blue and green curves, what definite integral represents the enclosed area? captured area, which would just mean this area right in there, right? What's it going to be, everybody? And that's supposed to be, here, that's supposed to be, whoops. That's supposed to be, I got to give you a, that's 4. Does that help? Yeah, that was probably confusing. Yeah. So what's it going to be? Becca, what are you going to get? There you go. It doesn't matter that the blue one's below the x-axis. It makes no difference. Green one's above the blue one. And so it's just going to be the integral of the top function minus the bottom function over the interval from 0 to 4, right? That's it. Okay. No harder than that. Okay. That's it. That's that area in there. Okay. Make sense? Okay. Other questions? Okay. All right. So I want to poke ahead a little bit with, I'm going to backtrack a little bit. This is a theorem that I chose not to really deal with earlier. I like to sometimes deal with these together. It just didn't fit with where we were in the class relative to vacations and things too. So we want to look at there's 2 different mean value theorems in calculus that are really, really important. These are existence theorems. We just call these MVT. You know, MVT is mean value theorem, and we just specify, are we talking about the mean value theorem for derivatives or the mean value theorem for integrals? So we talk about MVT, we just say MVT for derivatives, MVT for integrals. Here's MVT for derivatives. Okay, we build it through an intermediary. We're going to talk about Rowley's theorem first. And well, here's what it's another existence theorem. And existence theorems all work the same. We have an if statement, so if certain criteria are met, then the theorem guarantees the existence of something that we can then look for. We know it's there and we can look for it. Okay, so everybody quit what you're doing for a second, take a look at this. This is a pretty important one. We're not going to spend any time, I'm not going to give any problems on this one. We're going to move on to the just a tilted version of Raleigh's theorem is the mean value theorem. But here's what Raleigh's theorem says. Let f be some function that's continuous on the closed interval from a to b. So let's dissect these statements here. I want you guys to paraphrase that for me. So what does the underline part mean? What's that mean, Jonathan? Let f be continuous on the closed interval. What does that imply about me graphing that function? Discontinuity, right. So in other words, I could put my pen down on the board at x equals a and graph the function until I get to x equals b without ever picking my pen off the board. Okay, that's what the continuity implies. Okay, how about the second part? And differentiable on the open interval. So between the endpoints, it's differentiable. What does that mean? It's okay, it means that there are no sharp corners. And the other weird thing is there can be no vertical tangent lines, right? But the main thing is it's no sharp corners. Well, a lot of times this doesn't typically show up in high school books, but when I was in college, this was how all the professors would have talked about this. They would have called this the combination of those 2 criteria. You can meld that into one quality of a function called smoothness, right? We would say that f is continuous on the closed interval and differentiable on the open interval is equivalent to saying the function is smooth on the closed interval, meaning it implies something about the way this thing looks. I put my pen down at A and I graph it and I never have to do anything jagged. If I were to rub my hand along the function, I'd never get cut or scraped because it's never sharp, right? It's always smooth every place, okay? So if that's true, if it's smooth and if f of A is equal to f of B, So if the y coordinates at the endpoints are equal, then what's the implication? Well, the implication is there's got to be at least some intermediate value c between the endpoints such that the slope of the tangent at c is equal to 0, right? Doesn't that make sense? Because like, look at this. I thought I had a picture with this. Did I not? Oh my goodness, what happened here? Now I know I built a picture. Oh, there it is. Yeah, there it is. Okay. So here's a picture, right? Like if I'm starting with a y value of 2 arbitrarily, doesn't matter, but I end with the same y value, if the function is smooth, if it has no sharp corners and it's continuous, then I'm going to have to go through at least one point where the function turns. It has to go through either one interior minimum or maximum, maybe multiple, right? But it has to go through at least one where we have a horizontal tangent line. Okay, in other words, the slope of the secant line connecting the endpoints is going to be 0, isn't it? Because the function ends up where it starts off in terms of a y value, right? What does a secant line mean? A secant line is a line that connects 2 points on a curve, 2 distant points on a curve, right? The slope of a secant line is always equal to an average rate of change. What's the average rate of change of the function from x equals 1 to x equals 5? It's 0, right? Because the total change is 0. It starts at a y value of 2 and ends at a y value of 2. So over that entire interval, the rise is 0 and the run is 4. Rise over run is 0 over 4, which is 0, right? The average rate of change is 0. Does it mean that the instantaneous rate of change is 0 the whole time? No, not at all. The thing might increase and decrease and do all kinds of things. But there has to be at least one place in there where the instantaneous rate of change, the value of the derivative, is equal to the average rate of change, which is 0 in this case, because the starting and ending values of the function are equal. Okay, give me 1 to 5 on that. Does that make sense? Okay. Does it tell us where they are? No. We'd have to go find them if we want to, but it tells us that they have to be there. That's an existence theorem. We met the criteria, so Raleigh's theorem guarantees that there's at least one place where we're going to have a horizontal tangent line. Okay. See if you get, Tori, can you ask a question? If that, like, is there anything that would help clarify this for you? Okay, so it's used in fairly arcane situations. It would be used to say, well, here's an example of how we could apply it. Okay, here's a way. So let's say I start off in Pendleton. My car is at rest at a stoplight, and I end up in Hermiston exactly 1/2 hour later. Okay, and it takes me a half an hour to get there. Okay, what's my average rate of change? Yeah, I'm stopped at the endpoints, right? Let's say I come to a rest in Hermiston. It takes me a half an hour to go 30 miles. What's my average rate of change? Total of 30 miles in half an hour. Mm-hmm. No, my average rate of change, right? Because I'm talking about distance. I'm looking at how much distance did I cover, right? Like let's say what we're measuring here on the y-axis is my distance from home. Starts off at 0 and it ends up at 30. Took me half an hour to get there. 60 miles an hour, right? I covered 30 miles in 30 minutes, so that's a rate of 60 miles in 1 hour, 60 miles per hour, okay? Is my position function smooth? Has to be, right? Because I'm a physical being in a car that has mass, I can't just instantaneously go from 0 to 30. I have to go through every possible value of my speed to get from 0 to 30. It has to transition smoothly, right? There is no way my car could ever have a sharp corner, right? And that might sound weird, but for there to be like if I'm looking at, let's graph this, right? So we're graphing V as a function of, or no, sorry, not V, position. We're graphing position as a function of time. Okay, we'll call that S as position, right? So I'm starting off at 0 and I'm ending up out here at a position of 30 miles later. So the average rate of change is a slope of 30, right? 30 miles over 30 minutes, okay? It is impossible for me. I could take, an infinite number of different trajectories in this position time graph to get from there to there, but I can't ever do anything like this. I can't ever do anything like that, because to do that would imply an infinite acceleration, and that the universe would explode if that happened. It wouldn't. It's not possible, right? I could change the rate at which I'm changing position. My velocity could change relatively quickly, but even if I were to steer into a brick wall or something, it's not going to go to 0 instantly. It's going to happen over a period of like a second or something, right? And so no matter what, my position is changing smoothly. And so therefore, what do I know about this? Well, um, I guess I got to, oh man, we're doing Raleigh's theorem, aren't we? So I got to change this a little bit. Sorry, I got to go back and change the premise of we'll come back to this one for the mean value theorem. So now I'm going to travel along 84. I'm going to drive in my car along 84. All the traffic's been removed. I can drive both ways on the freeway, okay? And so I'm going to go 30 miles down the freeway, and then I'm going to turn around and come back, and I'm going to end up right where I started 1 hour later, okay? Well, what's my average rate of change? 0, because my final position is equal to my original position, right? If we're defining the positive direction as being towards Portland, let's say, and the negative direction as being backwards, that guarantees there's at least one time in there when my velocity had to be 0, right? Because my average velocity was 0. My average rate of change was 0 miles over 1 hour. I ended up right where I started. So at some point in there, I had to be stopped. I had to be going, my instantaneous rate of change had to be 0 because my position function is smooth. Well, that stands to reason. Obviously, I had to turn around at some point, right? So at some point, my car had to stop and I had to put it in reverse and start driving backwards towards Pendleton, right? Does that make sense? I can't instantaneously go from 30 miles per hour heading down the road to 30 miles per hour going back this way. Maybe it happened multiple times. Maybe I went kind of backed up, went forward, backed up. Who knows? But it happened at least once in that trip. Okay, that's kind of an application, I guess, right? How about if we generalize this just a little bit? So the mean value theorem, all the mean value theorem is saying now is that, well, let's not constrain this to where our starting value equals our end value. They could be different. But if the function is smooth on the interval from A to B, then there's going to have to be at least one place where my instantaneous velocity equals my average velocity. Okay, that would be the Hermiston example that I started. I was kind of jumping the gun on that a little bit, right? So if my average rate of change is 60 miles per hour, then there has to be at least one place on this trip where I'm going exactly 60 miles per hour. Has to be. Maybe I start off, let's say I start off going slowly because I'm at 0. Maybe I do something like that. Okay, that's my position time graph. So I start off with my speed being pretty low. It gets pretty high because look at that high slope right there, right? It gets pretty high and then it starts to level off and it goes to 0 and then it starts to be negative. I mean, there's all kinds of things that could happen, but there's going to be at least one place in there, at least one, where my instantaneous rate of change matches my average rate of change. Has to, for a smooth function. Everybody get that? There's no way that I could draw a smooth curve between that point and that point without having at least one place where the slope of the curve is equal to the average rate of change. In this case, there are two. That's the mean value theorem. Okay? Starting to make a little more sense? Okay. So mean means average, right? So there's at least one interior point where my instantaneous rate of change equals my average rate of change. Okay? Let's try this. I think it helps to see some problems. Oh, well, I guess I already drew a picture for that. I mean, if we needed to draw a picture, I mean, I just did. This is the picture, right? That's the picture. Only in general, we would say that this value is, that this value is A and this value is B. It doesn't have to be 0. And here would end up being one of my values that we'd call C. Here's one of my other values that we'd call C. Call that one C1 and that one C2. There's at least one value of C between A and B where the instantaneous rate of change equals the average rate of change. Okay, so here would be a kind of problem you're going to see. Would be something like that. Let's take the function f of x equals x times the quantity x squared minus x minus 2 on the closed interval from -1 to 1. So we want to see two things. First of all, does MVT apply? Do we meet the criteria? And if we do, then we're guaranteed at least one value of C. Now let's go find the values. Okay. So let's look at this now. Are the two criteria met? Is f of x continuous? Well, how might we maybe rewrite f of x in a way that's a little bit more convenient for us? Yeah, good. Distribute the x and just make it a polynomial. How about? Okay, so if we write f of x as then x cubed minus x squared minus 2x, it's a polynomial. What do you know about polynomials? Polynomials are everywhere continuous, right? There's no discontinuity. So we could check criterion number 1. It's continuous on the interval from A to B. Is it differentiable? Well, what's the derivative of a polynomial going to be always? Another simpler polynomial, right? So if we calculate f prime, it's just going to be 3x squared minus 2x minus 2. Okay, well, being differentiable means that the derivative exists everywhere. That's really all it means, right? Does that derivative exist everywhere? Yeah, right? And is the derivative, okay, yeah, okay, everybody buy that? The derivative is continuous on that interval, and therefore it's differentiable, okay? Do you see that this is another one of those relationships in calculus where we could say, okay, differentiability, well, all that is just continuity of the derivative. So the function is continuous, meaning it's continuous, and its derivative is continuous, which means the function is differentiable. Okay? Anybody buy that? Okay? So then we meet the criteria. It is smooth between -1 and 1. So now what would we do? Now we got to go find C. Now we need to find the places where the derivative is equal to the average rate of change. Well, what's the average rate of change? It's just slope triangle, right? It's the difference quotient, right? That we dealt with. Remember when we first started calculating derivatives, what did we do? We took the limit of the difference quotient as the spacing between A and B went to 0. We just merged the slope of a secant line. We morphed that into the slope of a tangent line by forcing those points to overlap, right? So we can calculate this. In our situation, A is -1 and B is 1, right? So our average rate of change is just going to be f of 1 minus f of -1 over 1 minus -1. Okay, we'll go back to our function f of x. What's f of 1? F of 1 is 1 minus 1, so 0, minus 2. -2? What's f of negative 1? Here I'm getting negative 1 minus 1 is negative 2 plus 2, right? So 0? Okay. So negative 2 minus 0 over 2. So my average rate of change is just negative 1. So what do I do then? Well, I've just got to set my derivative equal to my average rate of change and find out where that happens. I would just solve that equation. No big deal, right? Just solve that little simple quadratic equation. So I would just get 3x squared minus 2x minus 1 equals 0. And hopefully that's going to factor. Let's see, what am I going to get here? Does it factor that way? I'm hoping, yeah, it does. This would be a minus 1 and that would be a plus 1, right? And that would FOIL properly. So I'm getting the solutions either x equals negative 1/3 or x equals 1. Are those both solutions guaranteed by the mean value theorem? No, this one's not. How come? Say it again. It's an endpoint. Yeah, that's not what the mean value theorem says. It guarantees at least one value of C between the endpoints. So this is the one that's guaranteed. That one is not. Okay, make sense? Well, we know that the outcome is if we meet the criteria, then there's at least one value between the endpoints where the instantaneous rate of change equals the average rate of change. Yeah, average rate of change was negative 1. We calculated that. We'll say it again. Yes. Yes. Okay, make sense? Okay. Right. Light has no mass, so light can. Yeah, because that's called photon pressure or light pressure.